about brains and introduction.
Thanks. So, people were asking me whether or not I have notes and what have you, and the answer is yes. And I wrote them many years ago, and there they are. So there's this has everything I'm going to talk about today. I think is in that. If you want more, including stuff on ADS-CFT and stuff, all of that from the point of view of brains, there's a book you can get, also written by me from Cambridge University Press. But if you just want a quick thing you can get access to right now, just go online and to the archive. There's also some notes by Polchinski, Shori, and myself from maybe 4 years before, 96. It's called Notes on D-Brains, which are also possibly helpful. So, here you go. Okay, so let me just finish off what I was saying about the type 2 strings. So both 2A and 2B have dilaton, field, right? The 35, and the 28. And then 2A, right? This is the Schwartz sector. And then 2A has, and so I'm going to use a different notation from what I used before. I'm just going to put in brackets a number to represent the rank of that antisymmetric. So C's are always going to be antisymmetric, and I'll denote their rank like that. So if you recall, I had these guys are type 2A, type 2B, SCADA. I just want to pause here for a moment and note a couple of interesting things. So first of all, so we're in 10 dimensions. So what I can do is I can construct the field strength of one of these guys by taking a derivative. Okay, and then I can Hodge dualize and form a dual field strength, which in turn is the derivative of some other antisymmetric tensor field. Okay, and if I were to do that, then it's actually kind of nice to lay it out. You can then just sort of notice. So first of all, you notice that this guy is self-dual, as I had discussed before, and then I have something like that, and then I have C 5, 7. So Hodge duals. So that at this level is just a game we can play, and it's sort of interesting. Let's finish the game, right? Let me also call this, because it's antisymmetric. I can maybe also by analogy just call it B2. And hey, I can just do that too. I can polish dual eyes and also think about this creature. Okay. So right now, that's an interesting game we can play, and we'll come back to why that's a useful game later on. Any questions about that? Modularity? Okay. Good. What else did I want to do? Oh yes, and as promised, right. So this is the Ramon sector, and then I also said, again, 8 times 8 is 64, and so 8. I don't want to write it. In the Nova-Schwarz-Ramon sector, I have 8B plus 8C S plus 6C. And so, as I said, I could write that, in terms of fields, that would be something like that. A spinor, a fermion with just a fermionic index, and this, I guess the dot, recalling the notation George was using, the dot, alpha or alpha dot or undotted, is that SC choice, if you like. And Ramon Nova-Schwarz sector, so I have 8C plus 6S, and so on and so forth. So the point is that type 2A has 2 of these. That has 1 of these and 1 of these, right? Type 2A has 1 of each. And type 2B has just 2 of 1. Okay? And that's why it's the chiral choice. Okay, so what else did I want to talk about before we move on? Okay, let's given we're listing everything, let's also look at type 1 and have that up as well. And that had that had a mu, and it's some superpartner. Okay, there are a number of things that should suggest that we're not done yet. Okay, but before I do that, did you okay, actually, I'm just going to carry on. Okay, so there's something that should bother you about the type 1 string S-list. And so first of all, just knowing about string perturbation theory, just knowing how strings interact, should suggest that this is very incomplete, right? I have this open string sector, but as you know, I can consider a process in which the open string interacts with a closed string sector. Okay. In fact, the type 1 string must have some coupling to an open to a closed string sector. So in some sense, I haven't really listed all of the fields that are available yet. And so I'll sort of explain how that comes about, because that's going to be sort of interesting. And really, it would have been much better to have listed all of this over on that board, so that in a few minutes, when I complete that, we could add to it. So I'm just going to ask you to, in your notes, just have a page with this and this, and leave some room, because we're going to come back and finish the job of the type 1 string theory. Yes?
This is 10-dimensional, right?
Yeah.
So why isn't the 0 form dual to like a 10?
Why isn't the 0 form dual to a 10 form?
The Hodge tool, doesn't the Hodge tool do that?
Because 10 minus 2 is 8, right? So I differentiate, gives me that gives me a 1. So you're forgetting to form the field strength first, I think. Yeah.
I thought it was because of the D minus 2 thing you mentioned.
No, the different D minus 2. So let's do 4 dimensions, right? I have a 1 form, which is I have the gauge field, right? A mu, right? So I form F mu nu with a differentiation. Then I take 4. Then I take that 2 indices it has away from 4, giving me 2, and then I can take the D off that, giving me back a 1 form. So that's the 2 is those D's. I think that works. Yeah, and that's why this is self-dual. If I do D of that, I get 5. 10 minus 5 is 5. That's back to where I started. So it works for all of them. Okay, so first of all, let me first do something a little bit more interesting, make the type 1 string a little more interesting. Right now, all we've done is create a gauge field that at best has a U1 gauge symmetry. So first of all, let's enlarge the gauge symmetry. So did you do that with in your string course? Did you have? No? Okay, so let's do this first. Sorry, just go to the equivalent section. Okay, so this in the old language would be what we call chance pattern vectors. And we're going to go through it fairly quickly because we're going to have a completely different, a somewhat different way of thinking about it, which matches our sort of more modern perspective, if you like. But it does all come back down to this. So essentially, so I have a string, and we've already been studying the open string and the possibility of giving it some center of mass momentum, some amount k. Okay, and then we may or may not have excited some oscillators. Okay, but what I'm going to do is I'm going to add some extra, what seem to be fairly trivial degrees of freedom to the problem. Okay, so I'm going to add some non-dynamical degrees of freedom. To the ends. Okay, right now those degrees of freedom, as stated, are nothing more spectacular than labels. Okay, so I'm going to have a label I and a label j, and I goes from 1 to n. I, j, whatever labels those labels are, go from 1 to n, and then I'm going to sort of enhance my notation somewhat. Okay, I'm going to have I, j in my labeling here, momentum k. Okay, and then I'm going to expand this whole thing in some nice basis, which matches the fact that I'm trying to at the end of the day write down sensible amplitudes for how these strings might scatter and so on and so forth. And so in fact, I'm just going to have a Hermitian basis where so I have a matrix I, that matches the I and J labels of the strings. And so if you like, that's now my sort of more decorated animal. Wait, unfortunately, I'm using the same label A that I did for something else, but that was a different lecture, so no one ever remembers the previous lecture. So, yeah. Okay, and so the lambdas are Hermitian. So if you like, what I have is a sort of UN, this non-dynamical, if you like, a global, which is what it is. It's a global UN on the world sheet. Now, if you think about this, this is a really great candidate for a gauge UN in space-time. Because you remember that dialogue I keep talking about between world sheet and space-time, where I have the string world sheet, I do things on it, and then that whole thing gets mapped to points in space-time by the x's and the psi's. And so, if I then have a consistent theory in space-time where position is labeled by the x's, that global thing on the world sheet gets promoted into a local symmetry in space-time, which I would then call a gauge symmetry. Okay, so this is a really nice way of building a very large and interesting extra symmetry, which is local, a gauge symmetry in space-time. We're going to see different ways of thinking about it in the space-time picture when we come to D-branes, but right now, it really is just coming from adding this extra structure of labels expanded in this nice Hermitian basis on the world sheet. You might ask, why UN? Why can I not have other choices? We're going to see other choices come out later on. Okay, so I need some constraints on how these things work in order to give sensible physics. In other words, how does this show up? In physics, right? In physics, what I construct is amplitudes, right? I might scatter. I might have an open string. Let's do some special effects here. I have one open string. I have another open string, another one, and another one. Okay, and so in calculating, I'm guessing you probably didn't have much time to discuss scattering amplitudes, but maybe you discussed at least a little bit about how they might work. Some 4-point scattering amplitude involving 4 open strings then get somewhat decorated by this picture. So I have that string number 1, that string number 2, that string number 3, string number 4. Okay. But now I must keep track of the labels, right? I have I, J. Okay. So these are non-dynamical labels, right? So in going along the world sheet from here to here, I can't help but also have that this string's end is now also in J. Okay, then I can have K. Then this one must be K. Then L. And then this one must be L. And this one must be I. Yeah, so that's a constraint on the structure of how these things must show up in interactions. And if you think about it, that means that they only show up in the physics as a trace. Yeah, because so I have a factor. So this 4-point amplitude, were I to compute it, whatever content it has from the rest of the dynamics, it must have a factor hence the name factors. It must have a factor which would be, so there's a lambda ij from 1, lambda jk from 2, lambda kl from 3, lambda li from 4. Okay, so this is telling me that whatever I do with these factors, they come in traces. They come traced over like this. This is going to be a constraint in a moment on the kinds of things I can do when I act on them. I must respect the trace. Okay, so here we go. At this point, we can go to the 1970s and spend a lot of time doing some wonderful, interesting stuff with open string interactions and what happens with Champagne factors. And so let's not do that because we don't have time. And but you can then work out from various perspectives what's going on with all of this technology, and our suspicion that this gets promoted to a gauge UN in space-time, which our intuition about how worldsheet and space-time talk to each other suggested. Our suspicion actually is borne out, right? And that's borne out in the statement that if you were to summarize all the physics that you would get in low-energy interactions described this way, it would simply be UN Yang-Mills theory in 10 dimensions. Okay, and so there you go. So now I get to add a little bit to this, so let's have a UN gauge theory. This is a UN gauge multiplet in d equals 10, and yeah. Okay, so from some perspectives, you probably feel cheated that it's so easy to get a UN gauge theory, and yeah, it's really that easy. And you'll see why it's very natural when we think about this all in terms of D-branes later on. Okay. Oh, and then oh yes, that was the other thing I wanted to say. The fact that this respects the trace, that things respect the trace, naturally translates into how does the UN gauge theory work? Well, you see that it acts on lambdas by conjugation like that, and that nicely respects the trace. Okay, great. So we're still not done yet. That did not solve the problem of the fact that open strings are incomplete. And so I'm going to do one last thing before we get to D-branes. And that is, I want to go ahead and find the closed string theory that's missing for the open string sector. It isn't one of these. Right. So the picture you should have in mind, for example, is there's an open string. Oh look, it's propagating along. Okay. But nothing stops me from drawing a worldsheet diagram that looks like this, where there's some non-zero possibility of the open string emitting a closed string from the bulk of its worldsheet. So what is the nature of this closed string theory? We need to know it. Okay, it's not one of these. So there's a missing theory. So let me tell you what it is. So what I actually need to do is construct an unoriented string theory. especially with this Hermitian assignment that I've made here, you have a sense in which there's really a directedness to this string. There's an orientation. If I swap, then I complex conjugate well, Hermitian conjugate, and so on and so forth. And so there's an unoriented version of this that I quickly want to construct. So what do I mean by unoriented? Well, I want to look at the symmetry of, well, actually, sorry, let me start again. I want to look at the action of exchanging the string ends. Of the string, okay? So in open string call, I'm going to call this omega, okay? And its job is sigma goes to pi minus sigma, or in Z language, Z goes to minus Z bar. Okay, that's the thing that's going to swap that into that. Or actually, or confusingly, it's going to swap that into that, where that's the arrow taking me from that to that. That's sort of the joke. Okay. Let me do it this way. Okay. So we can just go through and see what happens to the spectrum of the string theory. Go back and look at the mode expansion and see how things operate under this exchange. Okay, so from the mode expansion, the center of mass of the string stays the same. The momentum stays the same. Okay, the alphas the even ones transform even, and the odd ones transform odd. And for the size, so, yeah. So right now, this seems like just a ridiculous exercise, but it will be really useful. Okay, so that's something I can work out. You can go and check that. Just look at the mode expansion that we had before. So what I'm going to do, if I define the string theory that is, if you like, a descendant of this one, I simply project onto stuff that's invariant under exchanging the ends. Right? That sector then will be a string theory that's unoriented. You can't tell between the. You can't tell whether it's pointing that way or pointing that way. Yeah, because I've thrown away all the stuff that could help you describe that, deduce that. So so project onto omega equals plus. Okay, so we can just do this at this level state by state and see what happens. So notice so do it state by state as we've been doing so far. But one of the things that will immediately bother you is that we spent all of this work finding this this master spectrum, which came from this. Okay. And according to that assignment there, this would get projected out of the theory, which is annoying, right? Because we like photons. Photons are our friends, right? Okay, and then all of that I did there would seem to have been pointless, and why bother? But we actually have an additional piece of technology available to us, which is that if under Chan-Patten factor, under exchanging the strings, we also do something to the Chan-Patten factors, then there's a possibility that we can preserve the photon, preserve the gauge factor under in the omega equals even sector. Okay, so that's what we need to do next. So let's just list that. Annoyingly, photon projected out. Unless omega acts on the lambda A factor. So how do we do that? Well, I simply need to propose how omega acts, and it had better act in a form like this. Any action I have on the lambdas had better respect the trace, and so I should act on the lambdas by some in a matrix, in a basis where I've written them as matrices. It should be some matrix lambda matrix to the -1. Okay, so let's just propose that and then write down what it must be. Okay, so omega on lambda ij j k, where k is momentum, goes to some lambda primed I j k would be what we get. Okay, and lambda prime then would be m to the -1, and if you think about it, because I'm also exchanging the ends of the string, this will now be lambda transposed, sandwiched in there. Okay? So let's just remind ourselves, because we're exchanging ends. So here's how we can actually figure out what that does. Right, we have one consistency check is that if I do lambda twice, I should get back to where I started. Yeah. So this must be true on fields. And so you can basically do this twice and get an equation. I'm going to work over here because I want to keep that summary. How about one for me? Done? Really? Anyway, so check. Let's go over there. You got one, right? Okay, thank you. Okay. Right, and so the lambda, if you check, goes to, if you do it twice, it'll be m -1 transposed, lambda m transposed minus 1. Okay. So this is telling us something very nice. Since lambda right, this is, for the whole set of lambda, it spans a complete set. A complete basis. Right, what I should have is that M minus transpose is essentially I guess at best I could say proportional to the identity. That's one or other of Scher's lemmas. I never remember which one. Okay, so I'll just say Scher. Sure. So that tells me that M is either symmetric or anti-symmetric. And we're almost done, because now we see some of the other possibilities I was telling you about. Okay, case by case now. Either it's symmetric, in which case M is M transposed, and proportional to the, I guess this notation for the identity, the n by n identity. How to write it? Let me just write it like that. Okay, and then so then, if lambda psi to the minus a half mu is even, then if you work it through, you see that lambda goes to just put this in, and lambda goes to minus lambda transpose. Okay, and the gauge group, the choice we have then is SON. Okay, so this is just working through the possibilities. The other possibility is that M is minus M transposed, in which case I can write it as I, and then the n over 2 in the off diagonal like that. And then lambda is equal to minus M lambda transpose. M is the even condition. And what we end up with then, depending upon which notation you want to use, we end up with either USB n over 2 or SP n over 2, depending upon. It's just that some people use the U, some people don't. Yeah. I guess I'm using the notation there where USB 2 is SU2. Yes. Yes.
Sorry, I got a little bit lost. So we first projected and the photon was taken out, right?
It would have been if we didn't have the Chan-Patten factors. So we're saying, but we have more than just the photon. We have lambda times this. So if we have a non-trivial action on lambda, then if we have a non-trivial action on lambda, then we can make this even if lambda goes to minus lambda transposed.
All right.
Right, so I wrote down in general how does lambda transform? It must be M lambda transpose n to the minus 1. And then I showed that M is either this choice or this choice. Yeah. So it's I could have just told you that, but I want to show you could actually work it out explicitly. And it'll also be extremely geometrical when we come to deep brains shortly. Okay, so we can go through, and 1 second, we can go through and we can play this game. We can construct then this unoriented open string theory with one of these types of gauge groups by carefully going through and making sure that we project out onto even omega. Yes.
You first stated that lambda was going to, but lambda prime was m lambda transverse m to the minus 1.
Yeah.
And then in the A option you choose m equals to the identity.
Uh-huh.
So
Yeah. So if I put m as the identity there, oh. Oh, you mean the minus sign? What have I done wrong? No, it's not.
There's a minus sign.
There's a, I think I.
One of the two i's n has. It doesn't affect the matrix.
No. You know, this is already the case in part A. So what did I do wrong? No. Sorry, it's because this is a mistake. This is an equal sign.
oh,
Right? It doesn't. It's not that it's transforming that way. Thank you. Very good. Thank you. M transforms it that way, but it then says, in order for this to be true, what must be left is that lambda transpose must be minus lambda. Thank you. Yeah. And so that's why it's an SON matrix. Yeah. Okay.
So,
Yes?
so I didn't hear his question, I just heard you trying to answer. But if that's m, and you transpose it, and you put a minus sign in it, and it's not equal to itself. So I guess there should be a minus sign on one of the two I and has block.
Oh, this? Okay, yes. Oh, yes, thank you. Thank you. Yeah. It's in my notes, I just didn't write it carefully. Thank you. Thank you, everyone, keeping me honest. Okay, so while we're at it, okay, why not why not just play this game on closed strings as well? Yeah, because we found a new game we can play. So let's do that. And it's not an idle game. As you'll see. Now, clearly, I hope, type 2b is the one that it makes sense to do this on because it has identical left and right sectors, right? It has the same chirality of spinor on the left and on the right. So I have a chance of creating something that has a symmetry effect, change to left and right, left moving and right moving. Okay? So let's make an unoriented closed string. Type 2b has same chirality on left and right. So let's play with that. So if you like, omega is a good symmetry. And well, okay. So the way to do it, if you wanted to go through and look at the spectrum, sigma goes to minus sigma, or z goes to z bar. And basically, untilted goes to tilde, and vice versa. Right, you have those independent left and right moving sectors. Okay, so we can do this. Now, the thing that we care about now is essentially we're acting on the left and the right. The things that we can be different could be also the indices, the space-time indices. Okay, so that's a nice way of seeing what happens. If you look at the type 2b spectrum, and you look at things in terms of how I've constructed them, right? For example, the massless sector, right? B mu nu, G mu nu, phi, right? Those come from having a psi minus a half, psi minus a half, and I have a mu and a nu here, right? I either have the anti-symmetric choice, which is these guys, or the symmetric choice, which is these guys. Yeah? So the anti-symmetric choice is going to get projected out, leaving just this stuff. Yeah? So we can see from the spectrum then, if I started just going through, we'd see that the type 2b spectrum has phi, B mu nu, and G mu nu. Okay, this gets thrown out. Okay, in the Ramond sector, right? I have C mu, mu, and C mu kappa sigma. Okay, those are the guys we saw. Actually, the opposite guys get thrown out. So you get the minus sign from the antisymmetry in the indices, but there's an extra minus sign because the fermions, remember this comes from the Ramond sector, and the fermions will throw you in an extra sign. So what actually happens when you trace it through is that these guys get projected out. So let me just urge you to go and trace it through, and trace that through, and warning, extra sign from fermions. Okay, and actually we're kind of done. Okay. Oh, and one of the supersymmetries gets thrown away. If you like, the Nova-Schwarz, Ramond, Nova-Schwarz. Take your pick as to how you describe it. One of them gets thrown away. So what do I end up with? I end up with a closed string theory that's missing a B mu nu, which is kind of interesting. It's missing those fields as well. And only one supersymmetry, and it's unoriented.
Sorry,
Yes?
is CU or just C?
Oh, thank you. Yeah, this is a scalar. Thank you. Did I write that down wrong there? No, I didn't. Okay, thanks. Okay, so it's a new string theory that looking for a home, looking for a job to do. Okay, and actually, if you were to work this out, and this will take me too far afield, but this is exactly what we need to be the closed string sector of the type 1 string theory. It has the right amount of supersymmetry now. Yeah, or only just one supersymmetry. It's unoriented, and so it can talk to an unoriented open string sector. And if you were to go through in detail and check the consistency, you would find that it has exactly the right sector needed to make the type 1 string theory a consistent string theory. So there are many other ways of seeing this. One way is that if you actually look at this theory from low energy perspective and simply write down the fact that it's a chiral theory in 10 dimensions means that it in principle has an anomaly, which you can compute, you find that it has an anomaly. Okay. This is a chiral theory in 10 dimensions that also has an anomaly. And you can get these two anomalies to talk to each other essentially through this field via what's called the Green-Schwarz mechanism. and that will actually give you a consistent theory. And what it'll do, it'll give you a consistent theory only if the gauge group is something appropriate to an unoriented string theory, and if that gauge group is SO32. So it picks out one of these choices, and it turns out to be this with that equals 32. And I apologize for the fact that I don't have time to do this justice. But like I said, my mission is to construct, is to teach you about D-branes and not construct all the 10-dimensional string theories for you. So you probably have heard about this or its cousin. Well, that's a spoiler, I suppose. The heterotic SO32 string theory. The fact that they're cousins. They don't have cousins, they're actually the same theory. That's a spoiler. Okay, so sometimes this is called the type 1B string theory, just for fun, or confusion. And so let me complete our table now. Right? I have the gauge multiplet. I have an SO32 gauge theory. And now I can draw diagrams like this, where I have an open string. It's going along, minding its own business, but it at one loop can couple to an open string sector. I now know what that open string sector is. It's this stuff. In a way, here's something else that's interesting. Okay, it's a string theory. It has a dilaton and a graviton. Okay, and it lost its antisymmetric tensor, which you kind of like all string theories to have. And in a way, what it does, it borrows it from the Ramond sector. In a way, it sort of still has one, but it's going from the Ramond sector. And that's kind of amusing. I will say more about this theory shortly. But anyway, so now we have all the 10-dimensional open and closed string theories, except that we don't, because we haven't done the heterotic string theory. But these are all the ones I want to talk about today with regard to D-branes. And I'm going to simply say that this is enough, because by strong weak coupling duality, I can get the rest. And hopefully, in your electric course on dualities starting on Monday, you'll see why that's not untrue. Are there any questions about this before I move on? Yes?
The open strings you're talking about are unoriented.
That's right. Yeah, that was the point of that. Yeah. In fact, they have to be. Yeah.
1D is just this part or the whole? What
Depends on who you talk to. There was no the annual synod on naming things in string theory did not come to an agreement on the naming of these sectors. Okay, so just trying to decide whether to talk about supergravity at this point. Maybe I'll leave that for later. Yeah, yeah. You've waited long enough for something completely new, so let's go to something completely new. I could mumble something about low energy sigma models and write down 10-dimensional effective actions and stuff, but we can do that later. So let's let's discover something new, or maybe new for a lot of you. It's called T-duality. T-duality is going to turn out to be, extremely instructive for many reasons. But it's also a prototype of a lot of the remarkable things that we think string theory is good for. In that it'll be a highly non-trivial statement in space-time, which results from something that's extremely trivial on the world sheet. So it'd be another example of, like we did here, we did something really, really simple with Chan-pattern factors, and then we have space-time gauge symmetry, which seemed amazing. So we're going to do something which, in a way, is even more remarkable. It's going to be a simple swap, just a little parity swap, as it'll turn out on the world sheet, and it's going to turn into something amazing in space-time. Okay, so that sounds like a used car salesman or a magician or something, but no, really. Okay, so let's discover it step by step. So let's look at closed strings. Okay, and let's just go back and look at our friend the mode expansion. So now I'm going to put it all together in the same mode expansion, the left and the right, but I'm still going to keep, just for fun, just to pretend, I'm going to keep the left and right pieces of the zero mode separate. Okay, I'm going to combine the momentum zero modes. Those logs will combine into just tau there. And then we get alpha prime over 2. I'll have alpha 0 minus alpha 0 tilde mu. There's a sigma there. And then there's plus all the oscillator stuff. Okay? So if you just go back and look at the mode expansion we started with in the last lecture for the closed string sector, and you add those two things, you can just check that this is what you would get. Okay? And I'm not going to care about the oscillators very much. They'll just come along for the ride for now. Okay, so as I said, P mu equals 1 over 2 alpha prime square rooted right, and this is momentum. Right? And the way I've written things here, I've been very explicit about this. This difference is going to be keeping track of winding. And that's going to be very important, so that's why I've made it explicit. And we'll see, we'll see right now why it's winding. Okay, so here's my string doing whatever it does, moving along. I have sigma going from 0 to 2 pi. All right, but it's periodic, right? Our string, yeah, in sigma. Right. So periodicity. Sigma goes to sigma plus 2 pi. Okay, I can just implement that. Okay, and that means that x mu will go to x mu plus 2 pi. Let's check. That's right. Alpha prime over 2. Alpha mu 0 minus alpha tilde mu 0. Right? All I did is I just shifted sigma by 2 pi there. Yeah. And so that's kind of right. So therefore, right? In order for that to be a symmetry. So, yeah. And this is what I would call so I put it back in there and my momentum collapses to that expression once I realize those two things are equal, except I have another possibility. What if, what if x, let's pick a direction, right? I want a spatial coordinate. Let me pick the 9th direction, just to make life easier. Because it's in my notes, and if I pick the 8th, then I'd have to be right. What if x9 was wrapped on a circle? Yeah. So I have I have this 10-dimensional space-time. One of them is time. 8 of them are flat directions that we've been discussing, but the 9th one is actually a circle. Just consider that. Okay. In other words, what do I mean by it being a circle? I mean that x9 is the same as x9 plus 2 pi, the radius of that circle, which I'm calling r. Yeah. So that is you probably did this with George, right? Baby's first string compactification would be to compactify on a circle. So we all learned that very early on in our string theory class, and you learned about some very important things there. So that's sort of an important first baby step, if you like, to all of this fancy stuff with Calabi-Yau and what have you. But we're going to see, even in this really simple example, that there's some really important physics. So I'm calling it a baby compactification, but it's sort of the prototype for so much. Okay, so this is it. This is the compactification, right? I can even draw that manifold. There it is. Okay, right. So there's a loophole in the argument here. For the x9 direction, I can do something extra. All right. If I do this on x9, then I basically can write that this 2 pi alpha primed over 2 alpha 0 9 minus alpha 0 9 tilde is equal to 2 pi. Now let's notice something else. Okay, it could be 2 pi r, but actually it could be any integer times 2 pi r. That's good enough. Yeah. So let's count how many times it's doing that, and let's give that a number. Let's give that a name. Let's call it W for winding, because that's what it is, right? It really is. There's the string. I'm going to draw the string as red now. I know they've been black before, but let's make them red. Because I've lost the. Oh, it's over there, but it's fine. It's too far. Okay. Right. So here I could have the string wind around the x9 direction. That would be winding 1. But actually, I can have it wind some integer number of times around that direction. Okay? That's not the most helpful diagram, I hope you agree. So let me draw a better diagram for you. Let me simply draw x9 like that. Make that the origin. This is 2 pi r. This is 4 pi r. This is sorry. Actually, I do want it evenly. Okay, and then I can simply draw that, or I can draw that, so on and so forth. Yeah. So the point is that the string, when I go from 0 to 2 pi in sigma, right, I get from one end of the string to the other. So sigma is still running from 0 to 2 pi, right? But x9, while it's doing that, can go several times around the circle. Okay, so for example, here is it going 3 times around the circle. So W there is 3. I'm doing this to death, right, and saying this again and again in many ways because that intuition can inform so much of what you do in more complicated examples. So this is really nice. Also, drawing this kind of diagram is going to be extremely useful. Any questions? Okay, so now we see. So let's just put the finishing touches on this. So omega is winding. No, wrong color. So omega is winding. And okay, and then, but we also have that momentum. Since this is a particle in a box, a one-dimensional box, momentum is quantized. Right, so P9 is quantized in units of 1 over r, which again, you know from, even before you did the harmonic oscillator in basic quantum mechanics class, you did the momentum is quantized in units of 1 over the size of the box. So I actually have two equations here. Right, I have, so this is P is this, right? So let me write that. 1 over square root of 2 alpha prime alpha mu plus alpha tilde mu 0. So I have two equations. Right, I have one for alpha, not mu, 9. I have one for the difference between the alphas and one for the sum of the alphas. The sum tells me about momentum, and the difference tells me about winding. Okay, so now we're in good shape. What I'm going to do is I'm going to solve for the alphas to make this more explicit. Do that here. So solve, and we get alpha 0, 9 is equal to the square root of alpha prime over 2 n over r plus omega over r alpha prime, and alpha tilde 0, 9 is the square root of alpha prime over 2 n over r minus omega. Questions?
Shouldn't it be also symmetric when we give more than 2 ways round in sigma? More than in sigma also, shouldn't it be symmetric in 2 pi times the integer?
In sigma?
Yes.
No, because sigma is just tells me where I am on the string, and so I just go around and then I'm back.
And if I go around again, shouldn't I be?
Well, I just go around in sigma. I just keep going around. So I have the string, okay, which is a physical object telling me where am I on the string. That's parameterized by going from 0 to 2 pi. And I just keep going around. But then I map that string into a circle in space-time, okay? And I can keep track of how many times that string is wrapped on that circle by saying, as I go once around in sigma, how many times do I go around in the circle? And that's all there is. So I have this. So why did I go to all this trouble, other than maybe to take this, which you've seen a million times, and sort of unpack it in this careful way? I did that because now I'm in good shape to address another important thing, which is what is the spectrum of the theory in the uncompactified dimension? Right, so I can think of this like I said, as a baby version of what you were doing with George, right? Which is that I have some 10-dimensional string theory, and I put it on some fancy space-time, and then I look at the spectrum in the uncompactified directions. I'm doing the simplest thing possible, which is I'm saying I just have a circle, and then I have, in the 9 remaining directions, I have some spectrum. So let's just work out what that spectrum is. Okay, we know how to do that. It's the L0 condition. And we just need to write the L0 condition, but separate out the stuff that talks about the 9th direction from the stuff that talks to all the other directions. So we want to write a mass formula in the remaining 9 directions. Right? That's a nice exercise that you can do. Let me just tell you the result. So what's the 9-dimensional spectrum? Okay, so L0. It looks like I'm doing it. Okay, so L0 gives me m squared equals 2 over alpha primed. So I keep the alpha 0 for the 9 direction part separate. Okay. Right? This m now refers not to p mu, where mu runs from 0 to 9. It's just 0 to 8, right? Because I'm interested in the 9-dimensional spectrum. Does that make sense to everyone? Yeah? Okay. So there's the rest of it, which I'm keeping here. Okay. And then the rest is just the stuff that comes from the oscillators, which, if you work it out, is in the closed string units we're using, it's 4 over alpha primed n, which is just the number operator counting how many things are excited, oscillators excited, plus a, right? So n is some alpha plus psi, the usual thing, right? And then L0 bar gives me m squared equals 2 over alpha primed alpha 0 tilde 9 squared plus 4 alpha primed and tilde plus a. Right, and the a keeps track of whether I'm in the Raman sector or the Schwarz sector as before. Right, so now we're seeing all the technology we developed in the previous lecture. We're now using it in a real example. Okay, so there's the condition, and then, as I said before, I have the sum and the difference. Actually, I talked about the sum. I maybe didn't talk about the difference. The sum L0 plus L0 bar is indeed the mass shell, the full mass shell condition. The difference, it actually turns in terms of constructing the spectrum, what it does, it simply is what's called level matching. It tells you that you should have the same number of, the same oscillator number as counted by L0 on the left and on the right. Yeah, it's called the level matching condition. So, so if you do that, I can just construct the sum and the difference and so on and so forth. If you do that, let me move to a new board. Won't need this anymore. Let me move to a new board, and what we're going to do is we're going to get something rather nice. I get m squared is equal to n squared over r squared plus omega squared r squared over alpha prime squared plus 2 over alpha primed n plus n tilde plus a on the left plus a on the right. And then the difference is 0 is down, sorry, n omega. Right, these are just the 0-point energies. I'm just reminding myself whether it's left or right, so on and so forth, either minus a half or 0. Okay, so this is my mass spectrum, and I heard George mention the magic words Kaluza-Klein at some point. So I'm guessing that he probably started off his whole discussion mentioning Kaluza-Klein theory. And actually, so you all fondly recognize that the first term is just the Kaluza-Klein sector that you expect. Right? The point is that if you remember what the whole Kaluza-Klein thing is I have an internal component of the metric, wrapped on a circle. I wrap on a circle the original Kaluza-Klein thing. It would be 5 dimensions, for example. One of them is a circle. One of those directions. Then I have, if you like, the off-diagonal parts of the metric become some gauge field, and the other internal stuff become momentum modes, which correspond to particles in the lower dimensions. They get their momentum from just being particles in a box, so it's n over r, and there they are, right? Smaller the circle, the more massive those states are. That would have been the original sort of attempt at getting our world from higher dimensional theories. You don't see those Kaluza-Klein particles because they're too massive, because the circle's too small. Yeah? Here it is. Okay? So just from the fact that the string it has some momentum in the 9th direction, it has some Kaluza-Klein spectrum. It can also do its usual oscillations, right? And here they are, contributing in the usual way to the spectrum. Okay? But in addition, string theory is not Kaluza-Klein theory. It has other stuff it can do. Right? And so you can see that there's a new term. Besides just oscillating, it can also wind on the circle. And if it winds on the circle, there's a whole new class of states in the theory. And interestingly, they get more massive the larger the circle is. So they do the opposite behavior from the Kaluza-Klein, thank you, modes. And that makes sense, right? Because the string has tension, right? 1 over alpha prime. Okay? So if you take a string and you wind it around a large circle, okay, the larger the circle is, the more energy is in that state. Right? So that's the intuition for why they behave that way with R. Again, then n and omega is integers telling me how many units of momentum, how many units of winding. Any questions about that? Because we're now going to notice something very interesting about this spectrum. So let me take some limits. Because before we do anything fancy, we should check that we get back what we expect in our what we expect before we did anything. So if we were just doing Kaluza-Klein theory, right? If we make the circle larger and larger and larger, okay, that tower of states should in fact become lighter and lighter, right? To the point where actually, let me draw it. Okay, so I have a set of states, the momentum states. I'm going to space them like that. And as the as the circle gets larger, what I should do is I should decompactify. I should go back to the original higher dimensional theory, right? It seemed completely reasonable. Take the circle to infinite radius. Okay, and that sort of happens because the spacing is set by 1 over r. Okay, and so what happens is I go large in r, this shrinks, and if you like, I have an infinite tower of these, but they all sort of come down and form a continuum. And what's that continuum? It's just the freedom to have any momentum in that now uncompactified direction. And so I'm back in the 10-dimensional theory, if I was just doing Kaluza-Klein theory. That make sense? Okay. So let's say that. So r goes to infinity. Momentum states form a continuum, and we return to d equals 10, at least as far as they're concerned. What happens to the winding states? The winding states, on the other hand, there's another tower of states. Excuse me. Right, so the winding states become infinitely massive, and more and more inaccessible. And so that's completely reasonable. As I take the circle to be very large, I should end up back where I started. Now, the opposite thing should be that if I take the circle to be very, very small, I should get really, really far away from the 10-dimensional theory. My theory should become more and more effectively 9-dimensional. Okay, that's the Kaluza-Klein intuition, and as you can guess, that's actually not going to be what happens in the string theory. So let's do it in a different color. R goes to 0. Well, you can kind of see what's going to happen. Whatever I said about the momentum states, I now say about the winding states. Right? The winding states form a continuum. Become massless. I guess I should have said that here too. These guys become massless. Right. And the momentum states become infinitely massive. So you would think, if I were to interpret this, right, if I were doing an experiment, if I was doing an experiment and I was doing my scattering experiments and looking at the masses of states and what have you, and I didn't know what was momentum and what was winding, I'm just measuring these states that are showing up in my fictional, idealized experimental apparatus, I would conclude that I was going back to 10 dimensions again. Because it's essentially the same spectrum. I have a sector that is forming what looks like a continuum that I would interpret as the momentum associated with some internal direction decompactifying. So what I'm telling you is that whether I whether I make the circle very large or the circle very small, the theory keeps going back to 10 dimensions. Okay? In other words, and what you can see, it does that because the momentum modes and the winding modes exchange roles in these different limits. And where one was doing one thing in one limit, the other one takes over that role and does the same thing. So it takes the theory back to 10 dimensions. So I said this in a number of different ways, and perhaps over egg the pudding a little bit, because it's hugely important. I want you to understand it because it underlies so much of the things we understand about string theory. And then I'm going to make an observation about why on the world sheet the difference between these two situations is extremely trivial, but you have this profound difference in the space-time picture. So, and the other thing is that, yes, this is radically different from Kaluza-Klein theory in the sense that the winding states are not present there. So any questions about that? Because this is sort of, fundamental. All good? Okay, good. So, let me make a couple of observations then. The first of which, oh, thank you, yeah. The first of which is that I can actually see that the spectrum has a symmetry. If I exchange whether I'm on a large or a small circle, or whether I'm looking at momentum or winding states, then the theory doesn't care. Yeah? And so that's the T-duality symmetry. And then, so in space-time, that's what T-duality is. So let's state that. Obsessive compulsive in me is to continue writing text in blue. So T-duality is a symmetry of the string theory relating large and small circles. Which really should have nothing to do with each other. Right? So, I have a theory on radius, circle of radius r, okay? And I have a theory on the circle of radius r primed, where r primed is alpha primed over r, okay? The physics of these two theories is identical. And what I do is I exchange momentum states and winding states. And they play each other's role in those two different theories. So that's the statement of T-duality. The most important statement so far in my lectures in faded blue. Is that all visible enough, or should I write it again? Sorry, let's get rid of this one. Okay. Okay. But let me now let me point out something quite remarkable, because if you look at it, all it is. And happily I left this up here. So, right that's the space-time picture. The world sheet picture is that I exchange momentum and winding, I exchange N and W. If I do that, you'll see all it is just alpha 0, 9. Exchanges with minus alpha tilde 0, 9. So it's just a little minus sign on the world sheet. Yeah. Now actually, if you go and carry out any of the string computations that you've been instructed to think about with regard to important scattering amplitudes and things we might calculate in string theory, that minus sign actually doesn't matter. Okay, if you look, for example, in the stress tensor, it comes with pairs of these things and things like that. So that minus sign is a little parity, a little one-sided parity symmetry that the world sheet theory has. that doesn't affect scattering amplitudes, doesn't affect any sort of the sort of physics you might think would matter, doesn't affect this mass spectrum as we've demonstrated here. And so that's telling us that why that's actually a true, it's not just a sort of perturbative accident, it turns out to be an exact symmetry of the full string theory. So let's just say that. So it's a one-sided T-duality is a one-sided parity operation on the world sheet. We can rewrite two more minutes? Yeah. We can rewrite the dual theory in terms of x primed 9 z of z bar equals x9 z minus x9 z. So we can throw that minus sign through the whole mode expansion, and the theory is unaffected. So that's quite remarkable, and that's going to be our starting point next time. But I just have one observation to make left, and that is that there is one interesting place where we saw alpha 0 I should also say that this translates through down to psi. In the supersymmetric case, this would also translate down to psi 0 and that getting an extra minus sign. Okay, and that was in the construction of the type 2 superstrings fermionic sector. Remember there, the Ramond sector was built out of those psi zeros. Okay, we kept track of what the psi zeros are doing because they were keeping track of the kind of the transformation properties of spinors in the 10 dimensions. Yeah. Our counting of minus signs there, or those plus or minuses, actually will get affected by this. Okay. Now, if I'm just doing the type 1 theory, not a big deal. It'll just take the 8s, the thing we called 8s, we now call 8c. Doesn't matter. Yeah? But when we made that choice about what was 8s and 8c, when we had already one copy, which was the difference between type 2a and type 2b, that sign choice will swap the choice we made. What does that mean? It means when you do T-duality on the type 2a string, you put it on a circle, you do all the stuff we just did, you look at the mass spectrum and everything. When you look at the fermionic sector, you'll realize that it becomes the type 2b string if I make the duality swap. Does that make sense? Because that duality swap changes our sign assignments such that what we were calling the 8s on one side is now the 8c. So if we had an 8c and an 8s for type 2a, for example, then that sign swap is going to make it now either two 8c's or two 8s's, and that's what we call the type 2b. Yeah? Or vice versa. So that's the other statement. In the superstring theory, in the superstring case, type 2a gets exchanged with type 2b. And that's all I wanted to say.
We have some time for questions.
I was wondering about the duality in the type 1 case. Because type 1 case you're saying about the oriented. theory.
Louder.
It's an unoriented theory, type 1.
Yeah.
That you have to choose.
It's also an open string theory.
Yeah.
So,
So I was wondering about the classification.
exactly. So let's set up my lecture for Monday, right? You could go, well, I should, by all rights, I should go and do this with all the string theories that we've been thinking about. But this clearly isn't going to work for an open string theory, right? Because I don't have a conserved quantum number called winding anymore, right? If I try and wind the string some number of times, but the open ends are just flapping in the breeze, they'll just unwind. Yeah? So clearly T-duality is not going to teach us anything about the open string theory. Unless maybe we find some way of tying the ends down. Aha! Right? Okay. Yeah.
Duality can be the Canadian.
Absolutely.
And what are the parameters, the analog of the radius, the Canadian?
It depends upon what cycle. So there are several different kinds of cycles that then have, well, submanifolds. Let's be more general. That have what's the word I'm looking for? Parameters associated with their size. So so those things can, under the right circumstances, be analogs of the radius of the circle. One obvious one is the entire size of the manifold itself. But it's a complicated manifold that has submanifolds, for example, which are P1s, the two spheres and things like that. Those can have sizes. And so there are analogs of T-duality for those sorts of parameters. It's a longer story than I have time to tell you. But George is still here. He can probably also give you some nice examples. A really nice, it's worked out really nicely, for example, for K3, the hypercalar case that George talked about. Is it the Fourier-Mackay decomposition? It's a nice way of seeing how the analog of T-duality works. So, with that and Google, you've got all you need.
Regarding the alpha 09 equals alpha 09 and alpha 0 kila 9 goes to minus 0. Is that okay?
Is this the question or a statement?
Yes, no, a statement.
Statement is on the board.
No, but is that okay? Because if you apply that relation on the first,
Yeah. I'll end up with this, but with these swapped, and so I need an additional minus sign.
Yes, but if you apply the relation with alpha 09 in the first one, you don't have signs changes.
Isn't it?
Thank you. Wrong color. Thank you. I said it right, and I wrote down completely the wrong thing, and thank you for catching me. The point is this. I mean, you get this right. If I swap these two, then clearly alpha 0 just stays as it. Thank you. Yeah. I did that deliberately to see if you were paying attention. No, I didn't. Right. So that, right? The fact that it's a one-sided parity means that it's acting only on one side. So that was a ridiculous thing to say and say that at the same time. This stays the same, this swap sign. This stays the same, this swap sign. I apologize, and I'm really glad that you caught that before you all went, because you're all spending tomorrow checking the calculations, right? And you were confused, so I'm glad. Of course. There's still some time left over now to go to the pyramids or whatever.
Another question.
You're describing this dynamical string. You mentioned that the theory is equivalent to
Yeah.
lambda A, ij are just like double matrices.
The what matrices?
Delta
What are the Gell-Mann matrices?
base of the
Oh, you mean the basic? I need to be careful. There's some dressing we need to do, but it's on the way there. Yeah.
which is that the short length
Yes.
and that is required to be
I use Scher's lemma on the m, not the lambda. But by virtue of the fact that the lambda is a complete set. Sure. Yeah. Which was the statement I wrote down right next to that. Yes. Yeah. Yeah. If you look in your notes, you'll see. Yeah.
No, wait, let's try that.